Okay, so here's today's plan. We're going to be going over trigonometric ratios. This is the second lesson of our trigonometry unit in Math 20-1. Here we go. So today's plan is we're going to review reference angles from last class. Then we're going to talk about finding the length of terminal arms. Remember, a terminal arm is just a fancy word for the arm of an angle. Then we'll review trigonometric ratios. That's sine, cosine, tan. That's a review of what you would have learned back in Math 10C. Then we'll talk about trigonometric ratios on the Cartesian grid. That's a whole new ordeal right there. And then we'll talk about exact values, which is also a whole new deal. It is a busy one today, so don't be afraid to ask for extra help. Obviously, if you're watching this video, you're either watching it online or you're watching it for the reason I recorded this. I am sick today. So with that, actually, I should also mention if I sneeze or cough or sniffle or make any other lovely cold-related noises, you're very welcome. But just bear with me during this. I'm going to try to do my best and stumble my way through this. But again, make sure you reach out for help, ask a friend, anything like that. Send me a reminder, whatever you need to do. Here we go. So reference angle review. Recall, these are the angles between the terminal arm and the nearest x-axis. And as I just mentioned a second ago, the terminal arm is just a fancy word for like the arm of an angle. So if you drew an angle, like if this was your grid and you drew an angle over here, that's your terminal arm. The angle is between that and there, right? Your starting position, right? Anyway, first question here, find the reference angle for 130 degrees. Well, let's start by drawing 130 degrees. If we were to draw 130 degrees on a grid, keep in mind straight up is 90. This one over here is 180. So 130 is probably just over here somewhere. It doesn't have to be perfect. You can kind of just estimate it there. If that's 130 degrees, the reference angle is the angle between that terminal arm and the nearest x-axis. So we're actually looking for this amount right over here on the left. Now here's the deal. We know that this over here is 180 degrees, but we know that this angle is 130. When you're looking for a reference angle, you just have to figure out the distance between your terminal arm and that nearest x-axis. So in this case, because it's 180 degrees at the x-axis over here, and we have 130 degrees on this on this terminal arm, the difference between those two is just the difference between 180 and 130. Namely, that would be 50 degrees. Because 180 minus 130 is 50 degrees. So 50 degrees, we can say that's our reference angle. And remember, a reference angle, we just use like this little theta symbol. That's what it's called, theta, just by the way, with a little r next to it. That means a reference angle. Theta is used for angles. Little r means reference angle. Anyway, let's do this next one, 290 degrees. Remember, down here is 270. This one's 180. This one up here is 90. Sometimes it's useful to just draw them in there. 290 is just going to be a little bit above this 270 here. So about right there, that'd be 290. Now the nearest x-axis is this one over here, the one at 0. So we just need to find the distance between this 290 degrees and the 0 over here. Well, just keep in mind, 0 is also 360 degrees. So really, we're just looking for the difference between 360 degrees and 290, which in that case, you just subtract the two, the larger one minus the smaller one, and you're going to get 70 degrees equals theta r. There you go. Last one here, 260. Once again, just draw this 270 straight down. So 260 is just over here. Our nearest x-axis is 180 this time around. So we're comparing 180 with this 260. Again, the difference between those two, you just subtract the larger one from the smaller one in this case. So the distance between those two is 80 degrees. So 80 degrees equals theta r. The nice thing about reference angles is the absolute most a reference angle ever would be about 89 to 90 degrees, right? You can't have a reference angle that's more than that. It just doesn't make any sense. So anyway, let's move on. So next one, length of a terminal arm. So suppose we had a terminal arm that passes through the point 3, 4. I'm just going to stop right there. I'm going to draw that real quick. 3, 4, that's your x and your y. So 3 is over here, and then 1, 2, 3, 4. We're going to put a dot right there. So you're going to want to follow along with that in your notes. Put a dot right there at the point 3, 4, and then connect it as best you can with a terminal arm. It's a little shaky, but you get the idea. Question's asking, how can we determine the length of that terminal arm? Give you a hint. It has a lot to do with triangles, right? So that we can actually utilize something that we would have done in the past in previous math courses. Think about how you could form a triangle using this terminal arm. The way I'm thinking about it is maybe using this length right here and then this length this way. Well, we know this length is 3 and we know this length is 4. just count the squares, right? 3, 4. We're looking for the length of the terminal arm, which is the diagonal here. Because this is a right triangle, we can just use Pythagoras. Remember, Pythagoras says a squared plus b squared equals your hypotenuse, which we call c squared. The hypotenuse in this case is going to be your terminal arm. The other two sides, it doesn't matter which one's a and which one's b, just as long as you throw them in. Let's give this a try. So a squared will be 3 squared, b squared would be 4 squared, c squared, we'll just call that c squared. That's what we're trying to look for here. So we'll say that's c. Squaring these first, we get 9 plus 16 equals c squared. That means 25 equals c squared. Long story short, square root both sides, and you're going to get 5 equals c. So in other words, the length of the terminal arm here is just 5. And to answer how could we determine that, we'll just set up a right triangle and then solve it like you usually would in previous math courses. Next example, find the length of the terminal arm passing through the point -4, -1. Same idea here. Matter of fact, probably a really good idea if you pause the video here and give this one a try. Okay, so I'm going to go over this one, right? Now, the one thing that might stump you on this one is the fact that these are negatives. It still works as long as you're really careful with how you square this. If you're not careful with how you square this, you're going to end up having a bad time. So -4, -1, that's going to be this point over here. Connect it with the terminal arm. That was really shaky, but again, you get the idea. If we make a right triangle, like so, we'll have -4 along this way and -1 along this way. We can still use Pythagoras to find our hypotenuse, which I can just call c. So we have -4 squared. Notice I put brackets around that for a reason. I'll explain why in a second. Plus -1 squared equals c squared. Now, the reason I put brackets around those is because we're squaring that side. So we're squaring -4 and we're squaring -1. If you don't put brackets around it, just with how math works, it just assumes you're squaring the number and then tacking a negative onto it afterwards. And that's not exactly how things work here. Anyway, so throw these in. -4 squared, -4 times -4 would be 16. -1 times -1 is 1. That equals c squared. So we'd have 17 equals c squared. This is where you got to square root both sides, but 17 is a pretty awkward number. So here's what we can do. We can say c equals the square root of 17 and call it a day right there. That's called an exact value. That'll come pretty important a little later on. That's an exact answer. Square root 17, there's not a better way we can put that. But if we wanted an approximate answer, we would actually have to literally square root 17 in our calculator, which you're going to notice is going to be an absolute nightmare of an answer. So we can do an approximate answer. Let's just round. It doesn't say what to round to, but let's just round to, let's say, the nearest thousandth, so 3 decimal places. It gives us actually kind of a funny number, 4.123. That's approximate though, right? The exact answer takes in recognition that the square root of 17 is an absolute unmitigated disaster. We call that an irrational number. But sometimes, you know what, we just want an approximate answer, and that's good enough right there. Anyway, excuse me, I'm just really dealing with myself here. Anyway, let's move on. So review of trigonometric ratios. This is just review of Math 10C stuff. I'll really kind of try to slow this down here because it's probably been a long time for some of you. In Math 10C, you would have covered the 3 primary trig ratios. We call them sine, cosine, and tangent. So in other words, just sine, cos, tan. That's how we can simplify this. What you might have learned back in Math 10C is this little thing to remember what does what. It's called SOHCAHTOA. SOHCAHTOA is just a really nice way of remembering what each of these trigonometric ratios are. I'll explain that in just one second. Just remember that sine, cos, and tan are used to find the missing angle and missing side measures in right triangles. So just like Pythagoras, this only works when you have a right triangle. I also want you to remember that sine, cos, and tan, they take in an angle measurement. They work as something called a function. A function has to take in an input and then spit out an output. So for instance, you might have something like sine of 30 degrees, and you throw that in your calculator and it spits something out, right? So sine of 30 degrees, notice it's taking in an angle. So you actually have to plug an angle into it in order for it to spit out an answer. Now back to the SOHCAHTOA thing. SOHCAHTOA is just a really, really nice way of remembering what each of these trig ratios are really doing. When we talk about something being a ratio, that means it's like a comparison from one thing to another. Oftentimes we express a ratio as a fraction, so a numerator versus a denominator. Sine, cos, and tan are no exception. For SOHCAHTOA, That's a really interesting way of memorizing that sine, which takes in an angle, I'll just say sine of theta, equals your opposite side, that's the O in SOHCAHTOA, opposite side, divided by the length of your hypotenuse of your triangle. So in other words, whatever sine 30 degrees is, that would tell us the answer to the opposite side of our triangle divided by our hypotenuse. And the opposite, of course, is just defined as being the angle right across, or rather, sorry, the side measure right across from that angle. Cosine, the next part is SOHCAHTOA. Cosine is AH, which means it's the adjacent side. So the side that touches the angle, but it isn't across from it, and also isn't the hypotenuse. It's your adjacent side divided by your hypotenuse. Lastly, TOA in this means tan, once again, taking in an angle, equals your opposite side divided by your adjacent side. I think, I don't have a formula sheet right in front of me, but I think these trig ratios are actually given to you in your formula sheet, but if they aren't, SOHCAHTOA is a really, really nice way of memorizing which one is which. We'll do a few questions using this today, of course. Don't panic if you're forgetting how to do this quite yet. We will get there. And we'll get there right here. Look at this. So first example, solve for x. This is a question straight out of Math 10C. We'll do this one together, so I don't think you need to pause the video here or anything. Just take an inventory of what's going on in this triangle right now. Clearly, it's a right triangle. Maybe I'll just put a little box right here just so we know. It's a right triangle, which tells us we can use sine, cos, and tan. We're looking for this side length x. X is not our hypotenuse here, right? The hypotenuse is this side over here. I'll even label it hypotenuse. So x is not our hypotenuse. We won't have to worry about that. We're given an angle of 40 degrees down here in the right-hand corner. You can notice right off the bat that x is the opposite side to 40 degrees. It's directly across from where that angle is. So maybe it's useful maybe just to say, okay, x is our opposite side. And then this side that's labeled 8, that would be our adjacent side because it's just next to the angle, but it's not our hypotenuse. So it's the adjacent. Adjacent is always the weird one. It's always the weird one to find. So if we're solving for x, let's just try to figure out what we've got and what we can use. Since we're looking for the opposite side and we have the adjacent side, we'd like to use a trig ratio that uses both the opposite and the adjacent. Well, if you look at SOHCAHTOA, the trig ratio that uses opposite and adjacent would be tan. So we can use tan to start figuring out what x would be here. Let me show you how to do this. So tan, which once again needs to take in an angle, there's our angle right there, 40. So tan of 40 degrees equals your opposite side, which is x, divided by your adjacent side, which is 8. Now, sorry to jump around here, but before we go any further, just take a look at your calculator real quick. Like just turn it on, have a look at it. And when you look at your calculator, if you got a TI-83 or TI-84 or whatever, if you press the button near the top that says mode, it should bring up this whole big menu. I want you just to make sure that one of the things, I think it's like the third or the fourth one from the top, it says radian and degree. Let me even write that out. Radian, and then there's a space and it says degree. Just make sure that degree is the one that's selected. And if it isn't, just use your arrow keys to go down and then use the enter button in the bottom corner to select degree. We're going to need to have degree selected here because all of the angles we use in this course are going to be in degrees, not in radians. Radians is another way of measuring an angle. You don't worry about that until Math 30. Anyway, so make sure you're in degree mode here. Let's jump back to the question now. Tan 40 equals x divided by 8. To get x all by itself, we just simply have to times by 8 on both sides. So we'll have 8 times tan 40 equals x. And then you can take this 8 times tan 40 and you can literally just throw that right into your calculator. It'll spit out an answer for you, no problem. So 8 times tan 40 equals, and what I got was, it doesn't say what to round to, but we'll just round to the nearest tenth for now. 6.7 equals x. And that would be our answer for this question. So again, if you got something different, that just tells me that you're not in degree mode. You'd probably be in radian mode, or you just multiplied something incorrectly. So just double check that for sure, right? Another thing is you'll notice it was kind of subtle, but I put the 8 when I multiplied. I put the 8 on the left-hand side. The reason I do that is sometimes people end up accidentally going like, oh, tan 40 times 8, right? So then it's thinking that 40 times 8 is your angle. 40 times 8, I think, is like 320. So what this is telling your calculator is it's like it's doing tan of 320. That's not what we want to do. You're going to get something totally different there. So it's always a good idea, any number that you're multiplying over, just put it before tan. The good news with multiplication is with multiplication, order does not matter. So it doesn't matter if you do it before or after. It just saves you a little bit of peace of mind. That's all. All right, so this next one, we're solving for x. This time around, notice x is an angle. That is kind of interesting. Once again, I want us to do this one together. I don't want you to do this one on your own. I'm going to identify my right angle first. It's right there in the corner. That means this 26 is my hypotenuse. And then compared to the angle we're interested in, 20 is our opposite side. And then we just straight up don't have an adjacent side. We just don't even care about that one, apparently. So opposite and hypotenuse, those are the side lengths we're working with. We're trying to find an angle. Write out SOHCAHTOA again. SOHCAHTOA. We're looking for something that has opposite and hypotenuse in it. Well, if you look at SOHCAHTOA, you can clearly see that's going to be sine. Sine is opposite over hypotenuse. So here's what we got going on. Since we're going to use sine, let's use our angle here. So it's going to be sine of x. That's kind of weird. Sine of x equals opposite, which is 20, divided by the hypotenuse, which is 26. Now, here's what's really weird about this one. Notice x is stuck inside of sine. It's a common thing early on for people to go, oh, well, I guess we just need to divide by sine on both sides. But it doesn't work like that. Sine isn't something that's multiplying anything. Sine is a function. So here's what we got to do to dig x out of there. If you look at your calculator, once again, if it's T83 or T84, you're in luck. If you find your sine button, you'll notice right above it in like the background print, it says sine -1. Sine -1 is often called inverse sine, right? And an inverse sine undoes a sine. Long story short here, if we want to get x by itself, we have to undo the sine. So we'll take inverse sine of both sides, because whatever you do to one side of an equation, you have to do to the other. So if we take inverse sine of sine x, that just cancels out the sines. Whatever you do to one side of an equation, you have to do the other though. So we have inverse sine of the whole thing, 20 divided by 26. And what's nice is you can throw that directly in your calculator, just like I've written it down right here. Inverse sine, which you're going to press second and then sine to get in your calculator. Inverse sine of 20 divided by 26. And once again, let's just round to the nearest tenth. I know it doesn't say, that's kind of a mistake. But anyway, rounding to the nearest tenth, I got 50.3, and I guess that would be in degrees. So 50.3 degrees. So there it is. That's how sine, cos, and tan worked. Hopefully you remember a little bit of that from Math 10, but if you don't, we'll have to practice and prepare that because that's going to come back around. So here's where it's coming back around already right off the bat. Suppose we had a terminal arm passing through the point 5,8. What is the principal angle of that terminal arm? Just remember, principal angle means like the true angle, as we normally would measure an angle here. So this is where we're going to kind of combine the concept we started today with this concept that we've just covered again, this one we reviewed from Math 10C. I think it's easiest if we just start by drawing a picture. If we draw a picture here, let's just do a little grid. It's called a Cartesian grid, in case you forgot. 5,8, we'll say is just like over here or something like that. Certainly is in the first quadrant though. And if we label this as a triangle, we can see that this is 5 and this is 8. What the question is looking for is the principal angle, which means starting from 0 degrees to wherever our terminal arm is. So it's just going to be the angle in our triangle here. So that's all we're looking for. So since we're just looking for the angle in the triangle here, let's identify what we got. Clearly our right angle is in the corner. That means this side up here is your hypotenuse, but it looks like we don't really care about the hypotenuse this time because it's not saying how long is your terminal arm or something. So what we do have is we have our opposite side right here, and we have an adjacent side over there. Once again, coming back to SOHCAHTOA, that's your tool to figure out which one you're going to use. Look at which one has opposite and adjacent in it. Well, once again, that would be the TOA, right? So tan. So let's see what we got. Let's just call this angle theta. You can call it x, you can call it whatever you want. I'll just call it theta. So tan of theta equals opposite. That would be 8 divided by adjacent, which is 5. Just like with sine, we have to get rid of tan. The way to do that is using inverse tan. So if we take inverse tan of both sides, inverse tan, there we go. That will cancel out our tan and it'll get theta all by itself. So long story short, theta equals inverse tan of 8 over 5. I'm going to plug that in my calculator right now. Give me a second. 8 over 5. We'll round to the nearest tenth, but what's nice is it just rounds it right up to the next degree. This is going to be approximately 58.0 degrees. There it is, right? So bottom line is, it's very much like that last question we just did when we were reviewing trig ratios. Very, very much like it actually. We're just applying it to a Cartesian plane. That's about it, right? So in other words, draw a picture of a Cartesian plane, just like I did right here, and then go to town on it. That's all there is. Okay, so this one is a little bit weird, but we'll go over it anyway, just to like kind of summarize this. For trig ratios on a Cartesian grid, let's just think about this in terms of the coordinates of a general thing on a grid. Now, you might be looking at this terminal arm right here and saying, oh, it passes through like 3, 4 or something, right? Just ignore that. I just threw this in just as an example. Let's just suppose we know it's going through the coordinate x, y for whatever x and y are. Now, if you set this up as a triangle, you'll see that x is going to be this side down here. Y is going to be this side over here. And then it says it wants the length of the terminal arm to be called r. So we'll call it r. I would imagine r would stand for radius, for instance. Anyway, if we are using just those measurements, no numbers in here, just letters, x, y, and r, let's try to come up with something for sine. Well, just remember, in SOHCAHTOA, sine is the so part. So that's opposite over hypotenuse. If you're looking at this angle, remember our angle is just down here, the opposite side would be y, and the hypotenuse would be r. So we can say sine of theta is opposite over hypotenuse, which in this case would be y over r. Again, looking at where our angle is, opposite is y, hypotenuse is r. Now let's try cosine. Think SOHCAHTOA, so ka, C-A-H. The adjacent side in this case would be your x. Hypotenuse, once again, is r. So since cosine is adjacent over hypotenuse, that's going to be x over r. Last up, tan. Tan again is TOA. So that would be opposite over adjacent. The opposite side is y and the adjacent side is x. So tan is just y over x. Whether that's useful to you or not, it still is nice just to kind of summarize it. And if you look back at the previous example we just did, you'll see that when we did tan, it was literally just y over x. Like if I go back real quick, tan was just y, which was 8 over x, which was 5, right? Not a huge surprise. So sine and cosine, though, they need r being the length of your terminal arm. So if you know that length of your terminal arm, then you're laughing, right? Anyway, moving on. Exact values. Okay, this is coming back as well. Exact values, again, are where you just leave it as a square root, right? Also, though, exact values when you're talking about trig ratios could mean you just leave your trig ratio as a fraction, right? Let me show you what I mean. This is way easier when you see it as an example than when I just try to explain it, right? So determine the exact values of the 3 trig ratios for a reference angle of a terminal arm passing through -4, 4. Most of those words there don't mean anything. You're just looking for exact values of trig ratios passing through this, right? Don't worry about like, reference angle just means you don't worry about the principal angle. You just worry about your little triangle you're going to form. You'll see what I mean. So first things first, I think we should draw -4, 4. -4, 4 is going to be 1, 2, 3, 4, -4, and then up 4, 1, 2, 3, 4. -4, 4 is going to be over there. Connect it with a line. And then see how you can make a triangle out of it. You could make it with your y-axis. I never do. I'm going to make it with my x-axis. I think that's always better. So if I make it with my x-axis here, there we go. There's going to be my right angle with the x-axis. And let's label these sides. This side down here is going to be -4. This side over here is going to be +4. And then we don't know the length of our terminal arm, but we certainly could find that. As a matter of fact, if I go back a slide, you'll see that the exact value of sine and cosine are going to require the length of that terminal arm. So you know what? On this one, let's find what that length of the terminal arm is. We'll find that length of r. To do that, we just need to use Pythagoras. Pythagoras is going to say -4 squared, once again, watching the brackets, plus +4 squared equals r squared. -4 squared is just 16. +4 squared is also 16. This equals r squared. 16 plus 16 is 32. So 32 equals r squared. Square root 32, and you're going to find that you end up in trouble. It's going to be 5 point something, and it's going to be a horrible, horrible decimal. This is where that term exact value comes into play, and you'll be thanking me for this because it actually saves you work. Square root 32, you literally can just leave that as r equals the square root of 32. That's it. You don't have to worry about any more than that. You just say square root 32, and you're done with it. You don't worry about it anymore. Awesome. Okay. Anyway, to polish this question off, though, believe it or not, we're actually almost done on this one. Finding the length of the terminal arm is often the hardest part. We want those exact values of those three trig ratios. And again, we're dealing with a reference angle, which is the terminal arm to the x-axis. So we're talking about this is our angle. You can call it theta r if you want. Let's start with sine, just because it's the first one you usually deal with. So sine of theta r, sine of that reference angle, that's going to be your opposite divided by your hypotenuse. So watch the opposite side here. The opposite side of this angle is going to be 4, and your hypotenuse is going to be root 32. So you can literally just say this is 4 over root 32. That's it. You don't have to go any further than that. It's an exact value of a trig ratio. You just leave it as a ratio. In other words, leave it as a fraction. That's all you got to do. Next one, cosine. Cosine theta r. Cosine theta r is adjacent over hypotenuse from SOHCAHTOA. Maybe I should even write that at the top there. SOHCAHTOA. So adjacent is going to be -4 over hypotenuse is root 32. There it is. Done. So if you see a question like that, done. You just use SOHCAHTOA and you're done there, right? Last one, tangent. Tan theta r. Well, remember, tan is opposite over adjacent. The opposite side is 4. The adjacent side is -4. And you could leave it as that, but let's not be totally lazy here. 4 divided by -4, that actually has a pretty easy answer. That's just -1. So why don't we just simplify that? We might as well. The other ones couldn't be simplified. They were too complicated. So let's leave that as -1. And I think we're good right there. Whew. Okay, so when you see exact values of 3 trig ratios, it just basically means first figure out your x, your y, and your r, right? So in other words, use Pythagoras. And then for your 3 trig ratios, just use SOHCAHTOA and write them as their fractions. That's it. Here's one more. I think this is the last question of the day. Oh, no, it isn't. There isn't quite yet. Never mind. I was getting ahead of myself here. Ooh. Anyway, this is one of the last questions of the day, though, that's for sure. Determine the exact values of the 3 trig ratios for a reference angle of a terminal arm passing through 5, -3. Basically the same as the last question. So much so, as a matter of fact, I'll say, why don't you pause the video here and give this one a try on your own. Okay, now I'm going to go over this one. 5, -3. Just like before, let's draw this in. 5, -3 is just down here. Draw the terminal arm connecting it. Doesn't have to be super perfect, but you get the idea. Draw a right angle, or a right triangle, I should say. The right triangle should always be with your x-axis. It just makes things way easier. And then label this triangle. So this is going to be 5 this way and -3 that way. Just like before, because we're dealing with the 3 trig ratios, sine and cosine need a hypotenuse. So let's find how long that hypotenuse is. 5 squared plus, in brackets, -3 squared equals r squared. 5 squared is 25. -3 squared is +9. This equals r squared. 25 plus 9 is 34. 34 is r squared. 34, just like 32, not very nice to square root. So why don't we just say r equals square root 34. If it was a nice number to square root, then square root it. Like if it was 36, we know the square root of 36 is 6, but it's not a nice number, so we'll just leave it as root 34. So root 34 is our hypotenuse. Let's wrap this up. So sine of theta r, that's your reference angle right here, theta r. Remember, sine is opposite over hypotenuse. Opposite looks like it's -3, -3. Hypotenuse is, of course, root 34. There's one in the bag right there. Awesome. Next one, cosine theta r. Cosine, SOHCAHTOA, that's adjacent over hypotenuse. Well, the adjacent side is 5. The hypotenuse is root 34. There's another one done. Awesome. Last one, tan theta r. Tan is opposite over adjacent. Opposite side here will be -3, and the adjacent side here will be +5. There it is. Now, I mean, you could simplify that, -3 over 5. You could say, oh, that's like -0.6. Don't bother, though. Just leave it as a fraction. It's fine. If it's simplified to a nice number, like an actual whole number or an integer, go for it. But in this case, don't bother. Okay, just to summarize here, there's a relation between the sign, positive or negative, of a trig ratio and the quadrant it is in. You might have noticed some of these previous examples. Some of them are positive and some of them are negative. In this example we just did, sine and tan were negative, but cosine was positive. What the heck? Well, let me just tell you. So, oops, went the wrong way. Here we go. There is a relation. We call it the cast rule. Some people call it other names, but cast rule always works best for me. The cast rule basically is just a rule with the grid that tells you what is positive where. We'll start down in the bottom right-hand corner in quadrant 4. This is the C quadrant. That means cosine is positive down in that quadrant there. Quadrant 1, the one that we always like using, that's our A quadrant. A is going to stand for all. That means all trig ratios are positive up in quadrant 1. This quadrant over here is your S. That means sine is positive there, but everything else is negative. And then the one down here is T for tan, of course. That means tan is positive down there, but everything else is negative. So it's called the cast rule because if you follow it through kind of in like a circle there, it spells cast. Huge surprise. I don't know. It works for some people, it doesn't work for everyone, but it's just a good way of remembering where things are positive and where things are negative. And if we go back to some of the previous questions, you looked at, in this question, we were down here in the C quadrant, and notice the only thing that was positive was indeed cosine, right? Go to the example before that, the only one that was positive was sine, and that's because we were in the S quadrant, right? Kind of a big coincidence, it seems, but it isn't. It's just how math works. No big deal. If we go back to this very first example, maybe even one before that, this one right here, sorry, this one, where we're 5/8, everything would be positive there, because if you did SOHCAHTOA on this one and found it all, it would all be positive. Nothing's negative there. Anyway, I'm rambling. So let's get this done. Cast rule is what it is. If it works for you, great. If it doesn't work for you, whatever. You can see it if you just do the exact values of the trig ratios. But it is pretty useful. At least it will be. Anyway. There we are. We're done. Thank goodness. So page 96, questions 1 and then 3 to 14. Give those a try. Make sure you're checking the answers at the back of the book as well. And use each other as a resource on this one. Again, I apologize for those who are watching this in 2021 that I'm not there in person, but it is what it is. So anyway, best of luck. Contact me if you need.